Yes.
All right. Today is 17th. All right. So let us look at briefly continuous functions again. Right. So now, since we'll be taking subsets of Rn, so we should do this the definitions and few properties in terms of metric spaces. Suppose f from a metric space x comma dx to y comma dy be a map. F is said to be continuous at some point a in x if for every epsilon greater than 0 there exists delta greater than 0 such that mod of instead of mod we should write d x a comma x less than epsilon less than delta implies dy f fa comma fx. Actually, I should write symmetric, no problem. But to match with the usual definition, let me go with this less than epsilon. Right? So in case of R, you have modulus. So you get back your continuous functions on real line. Right? So in this case, see, the point is more likely or generally what we consider x and y to be subsets of Rn. And d would be this dx dy would be the restriction of the usual distance in Rn. Then you have to consider open sets, closed sets inside the set. What I discussed last time as a relative topology. So therefore, it's better to consider this definition in terms of metric space. All right. Now, of course, you know examples of continuous functions. That is not a big deal. What is more important is a characterization. So f from x comma dx to y comma dy is continuous. So what do you mean by the map to be continuous? So put it here. F is said to be continuous on X if F is continuous at every point x in x. All right. So here we f a map from x to y is continuous if and only if inverse of v is open for every open subset v in y. Is the statement clear? Have you seen this statement before? Anybody? Yep. PhD students will be, of course, would have seen it.
Yes, sir.
But so third year students, have you seen it?
Yes, sir.
Okay, so it is done in your analysis one course.
Yeah, analysis one. Yes, it was done in analysis one course.
Okay, that's good. So this is very important. This is very important. This is very important, and this will be useful to show something is continuous or use it whenever needed. All right. Do you remember proof of it? So assume first this side. Assume f is continuous. Continuous means in this sense. Continuous. To show, and then let's say, yeah, to show f inverse v is open for every v open in y. So this is open in x. All right. So that means you need to show that any point of this set is an interior point. So let x naught belongs to f inverse v, right? We need to show that x naught is an interior point. So which means a neighborhood of x must lie inside. A neighborhood of x naught must lie in the here. Now use the definition of continuity at x naught. So what you need to look at is the following. The continuity at x naught gives you that for every epsilon, right? So, I mean, before going into the definition, let me put this one. If x naught lies in V, and since V is an open set in Y, there exists epsilon greater than 0, yeah, such that collection of all Y such that d of y comma fx naught less than epsilon, this set lies in V. All right. Now we consider this epsilon, this particular epsilon. So for the above epsilon greater than 0, there exists delta greater than 0 such that this is by continuity of f such that is it what? Such that d of x dx x comma x naught less than delta implies dy fx comma fx naught is less than epsilon. All right. Now, what does this mean? What does this mean? This means collection of all x in x such that dx x naught less than delta. This set is contained in where? Yeah. Well. Here it is. So we need the image of this one lies inside collection of all y such that d of y comma fx naught less than epsilon. Is it correct? The last statement? Is it correct? So what we are trying is, let me try in a picture. So here was, let's say y, and this is x. And you have map f. Need not be 1 around. So we consider an open subset here. This is V. And F inverse V is a set somewhere here. F inverse V. And you want to show this is open. So what do you need to look at? You look at a point here. So you look at a point here. Of course, the image would lie somewhere here. And you want to show this is an interior point. Right? Now, so what does it mean? It means that there exists a neighborhood whose image under F will go inside here. Right? This red ball here should go inside V under F. That's what it means. Now, how do you get this one? We should get it by continuity. So the point is here, we look at a ball here in Y of epsilon radius. See, this is epsilon. This is epsilon. Now this epsilon, so here you see, so this side, this is the continuity. So this side means that fx lies in epsilon ball of fx naught. Whenever x lies delta ball of x naught. Right? So balls are with respect to the corresponding matrix. Right? Now here, by definition, whenever, so you get for this epsilon, you get a delta. So for this corresponding to this epsilon, you get a delta greater than 0. And you consider this to be delta. Right? This one to be delta. Now that one, by definition of continuity, this delta ball, the image of delta ball will lie inside the epsilon ball, which lies inside. So is this clear? The picture. This is what we did. Nothing else. We just wrote in terms of the language of analysis, and this is the picture. Yeah, any question here? Is this fine?
Yes, sir.
All right. Now we want to look at something called connected set. So I don't want to go. If you want to go beyond this further in continuity, you can look at Rudin's book. And if you have any problem in reading, you can tell me. So let us go to the definition of connected sets. So connected sets. So somehow you see, I mean, you want this to be somehow joined, right? So connected would mean like that. Okay, it will mean like that. But before going into further, let us just define something. It's a definition. So here, connectedness is defined in more general topological space. So the definition will give for topological space, but we will not use any arbitrary topological space. Maximum we'll use the matrix spaces. Okay. So let X be a topological space. So a topology is good enough to define connectedness. A separation of X is a pair U V of disjoint open subsets
Sir, one
of
thing.
X. Yes.
So the previous theorem, was that all there was to it? We had to show that F inverse V is open, right?
Oh yeah. So other part you forgot, right? Do you mean the other part?
Yeah, that too we didn't.
Yeah, you're right. Just a minute. Let me put it behind. Yeah, let me just complete this definition such that X equal to U union V. All right. Yeah, so continuity implies for every V, F inverse V is open. You need to show the other way also, right? I mean, you should tell me immediately. What about the other side? All right. So given F inverse V is open for every V open in X, for every V open in Y. All right. To show F is continuous. Right? So how do you show it? So choose epsilon. So consider a point. Let P be a point in X and epsilon greater than 0, right? Then you consider collection of all y in y such that dy y comma fp is less than epsilon. So is it an open set? Yeah. Is it open set in y?
Yes, sir.
All right. So B is an open set in y. So this implies by assumption F inverse V is open, right? So that means and P belongs to F inverse V, all right? So since P belongs to P inverse V, P is an interior point of F inverse V. So that means there exists delta greater than 0 such that collection of all x in X such that d of x comma p, so dx here less than delta is subset of F inverse V. Yeah, fine. Is this fine? So this is the delta neighborhood of one of the point P. So this implies for the above epsilon greater than 0, there exists delta greater than 0 such that dx dx xp less than delta implies dy fx fp less than epsilon, right? Hence f is continuous at p since p was, we need to go little down here. Since p was chosen arbitrarily, f is continuous on x. So is this fine now? Yeah. Is this fine now? This is nothing, just you need to just write things up. Unfolding definition. So this connectedness, have you seen connectedness in your second year?
No, sir.
Okay, so this is a new concept then. So you have a topological space, which means that you have the notions of open sets. So you know the open sets. So a separation of X is a pair of open sets U and B. So open in X. So that is important. If X is a subset of Rn, you cannot take open subset of Rn. It has to be open subset of X. So keep that in mind. So we are considering a topological space and a separation of a topological space. Well, in your case, it would be just metric space with the standard metric restricted to the subset of X. So U and V will not be the subset of the ambient space. It would be, so whatever subset you are considering to show connectedness. Right? It is the open in the subspace topology. I'll give an example once I define properly. So space in the sense topological space or metric space, whatever you choose, X is connected, so topological space actually, if there exists a separation pair of disjoint. Here one other important thing I missed, non-empty. Okay, so this is very, very important. So this part is very important. So people often forget to show non-emptiness. So this is important. All right, if there exists a separation of X. So now look carefully this one. So look carefully this one. What does it mean? It means U and V, of course, both are open sets, right? So X equal to U union V. It means U complement is V, right? So U is open set. What would be the complement of U?
It's closed in X.
Where it should be closed in X, but V was also open, right? So this implies V is closed, and similarly V complement is U. This implies U is also closed. So this implies U and V both are so closed in X, open as well as closed subset of X. All right. So what does it mean? So what does this connectedness mean? Let me write it here. A space, a topological space is connected if and only if the only subsets of X, topology space X, that are both open and closed are the whole space X and empty sets. So do you see it? So this is important to understand, that you don't have both open as well as closed set which are proper subset, proper non-empty subset of X.
Sir, I think in the definition you wrote that it's connected if there exists a separation. You mean to say if there doesn't exist, right?
Oh yeah, that's true. Yeah, thanks. If there doesn't exist separation, right? Yeah, true. So this separation means disconnected. It's not connected. Yeah, thanks.
Sir,
Yes.
I just had a general question. Like now that topology has been introduced, we can see almost all the
Mhm.
concepts that we studied using distance have been
Mhm.
somehow transformed into open sets. So, is it true that in analysis, almost everything that we study doesn't really deal with distances? All it deals with are open sets. Open sets and closed sets.
No. In analysis, it's basically mostly deals with distance. So so when you look at the open sets only, you don't have distance. You don't have analysis actually. Most of the things goes into topology. So whenever there is something like analysis, you don't have a sequence unless you have concept of distance, right?
Okay, yes, that's crucial. Distance is crucial for having a sequence.
Right. So distance is very, very important. So most of the time you will be dealing with spaces which have distance. So the spaces which does not have distance, those are quite pathological. You can't do much. But yeah, there are some things, some topological notions which one studies. So you'll see some things in your topology course, and then there will be some things in algebraic topology course, and you will see they won't use distance as such. But when you do analysis, there should be distance. There should be epsilon and deltas, and those things are not there if you don't have distance. Yeah, any other question? Example. So with this definition, examples a little bit difficult. So firstly, let's look at interval AB in R. So what do you think? Is it connected or disconnected? Disconnected is when it is not connected.
It's connected.
It's connected. How do you prove it?
Like the idea is, if there are two open sets O1 and O2, such that the disjoint open set such that the union is A comma B. I mean, that can't happen because there will be one point between O1 and O2. That point will not be included.
How do you get that point?
Like let's say O1 is A comma C and O2 is C comma B, both open. So C is not in
Yeah.
AB.
Right. C is not in.
Open AB.
Yeah.
C will not. Sorry. C will not be in the union. C is of course in open AB. C will not be in O1 union O2.
Right. So what kind of O1 union O2 you are taking?
Intervals, like O1 is an open interval and O2 is an open interval. It's I1 and I2. The I1 is open A comma C and I2 is open C comma B. When you take the union of these two, C will not be contained in that union, but C is an open A comma B.
Yeah, that is true. That is true. So so that means it cannot be written as union of two disjoint interval, open interval. Right? Does this prove everything?
Uh, Maybe we are missing something like how do we know that this is the only way of taking two intervals? Like,
That is true.
there may be other ways. I think that's what we are missing. Like, I can see that we can see that we have to miss a point if we want to express it as union of two open intervals. We will miss the point in between these two intervals.
That is
But
true.
I can't see how to prove that this is the only way of choosing two open intervals in that way.
Well, are the all open sets of R interval AB are open intervals?
Yes, all open sets in R are open intervals,
No, that's
except the
not true.
trivial open sets.
So any open set is an open interval.
Yes.
Do you agree? Everybody agrees?
No, the unions of arbitrary unions.
Right.
Achha, arbitrary union.
Arbitrary union. Arbitrary union of open intervals are also open. So you need to consider those as well.
So
Like the idea
suppose,
is, yeah.
so suppose that U and V is a separation of this interval.
Mm-hmm.
U and V are non-empty. So pick, say, x1 and x2, x1 in U and x2 in V.
Mm-hmm.
Look at the closed interval x1 comma x2
Right. That is
and
true.
intersect this with one of, say, intersect this with U
Right.
and take the supremum of this. That element will not be in the union.
Right. So that
This
is
was an
actually
exercise
the
in
idea.
analysis 1, I think. This was a homework problem.
That was an homework problem. Okay, so maybe I should give the following as homework. So it actually characterizes all connected subsets of R. Show that a subset E of R is connected if and only if the set E, it has the following property. Which is if X is an A, Y is an A, and X less than Z less than Y, then Z must be is an A. Okay? So this exercise show you that interval closed, open interval AB is connected, closed interval AB is also connected, right? So whenever X and Y is there, the whole interval must be there. The idea is as before. Suppose E is not connected, you get a separation, and you look at the intersection with look at 2 points into two disjoint open sets, and then you look at closed interval X comma Y and intersect with the first one, and look at supremum, and try to see whether that supremum belongs to which set, some subsets of separation or not. That would give you things. So you said somebody said it was an exercise in your analysis 1 course, right?
Yes, we didn't have the concept of connectedness, but this was the exact problem.
This was the exact statement, right? Or this was the thing. The connectedness concept was not there. So it was. So what was it here?
Cannot be expressed as the union of disjoint non-empty open intervals.
Oh, okay. Oh,
Just that.
okay. Okay. Yeah. So it is already connectedness is already done. You are looking at looking at for the second time. So this is good. So do this exercise. So this exercise is very important. So very important. All right. So now we'll go another notion of connectedness, which is called path connectedness. So first of all, what is a path, right? And here we look at inside Rn only, not in a metric space. So definition: a path gamma is a continuous map gamma from closed interval AB to, let's say, Rn. Path in Rn, right? Path or curve, whatever. So you have point A, point, let's say, so you have interval AB, and this is, let's say, gamma A, and somewhere it is gamma B, and you have some path, some continuous, right? So we have defined what is continuity between two metric spaces. Here you consider metric space in closed interval with respect to the usual metric in R, and then you consider Rn on the other side with the standard distance. So this is important. So, and this is geometric, very geometric. So you have what you need is just you have to have path. So can you give an example of a path? Yeah. What do you think the first path?
The identity map?
Yeah.
Identity map on an interval?
So identity map doesn't work really, right? So in Rn, if you look at, so you give it in general Rn, not in just R. Okay.
Just the constant function, I guess.
Constant function, yeah, it's a trivial path, right? You are standing at one point only. You're not going anywhere. So it's a trivial path. So first thing first geometric thing from A to B,
Straight
let's say,
line.
right. So let's say, yeah, x0 to y0. You just go in a straight line. Yeah, right? So gamma is a straight line. So what would be the equation, or what would be the formula for gamma? So gamma, you can take 0, 1 to Rn. So this x0, y0 is in Rn and En. So what would be the formula?
Tx naught plus 1 minus ty naught.
Right. So that comes from y0 to x0. If you want to go from x0 to y0, you just need to put 1 minus t x0 plus ty y0. So if you go from x0 to y0, or you come from y0 to x0, then you just t x0 plus 1 minus t y0. And you see these are continuous map. This is a linear map in T, so you have no problem. The straight line path, the straight line. Right. Second example, of course. Let's go into R2, but you can do it in Rn also. So this is cos t, sin t. So what is it?
circle.
Right. So you can actually instead of 2 pi, so here instead of 2 pi you can actually make it, let's say some what, alpha less than equal to 2 pi. Then this would be a circular arc, right? So you start from here and go. Say this is from 1 to some point here, which is gamma alpha. So if alpha goes to 2 pi, it will be closed circle. All right. Example 3. Gamma from, let's say, interval AB to, or let's say, yeah, AB is fine, to R2. Gamma T is equal to T comma T square. So what is it? Yeah. So what kind of curve is
Section of
this?
Parabola.
Yeah,
Parabola.
it's some part of parabola. Depends on, yeah. Some part of parabola. May not be the full one, but you can. It depends on what is A and B. You're going somewhere here. So you're going. It's a parabolic. Curve. So it goes along the parabola. So similarly, you can look at ellipse. So this coordinate geometry comes handy here, and these things can be taken to this is not just in R2. You can think of in Rn, in some plane in Rn, the same thing can be seen. For example, if you look at gamma AB to R4, you look at the same curve 3, but now in R4. So gamma T is T comma T square, or maybe let's say 0 comma T comma 0 comma T square, right? So it's in one plane in R4 and looks like parabola. So one can actually, this coordinate geometry, the curves in coordinate geometry I've learned, that comes really handy here. Doing analysis of these things. Okay, let's go into the definition of path connectedness. You perhaps already guessed. Let me put here since we have not defined the general curve, we have defined for Rn only. This is true in any topological space either. So you can think of path connectedness in any topological space. So path will be from AB interval to that space X. But here, let's expect our intuition in our Rn, which one can see. So a subset E of Rn is said to be path connected if for every two distinct point x0, y0 in E, there exists a path gamma from AB to Rn. Oh no, here is the subspace topology coming into the picture. AB to E. So path should be in E such that gamma A equal to x0 and gamma B equal to y0. Like for example, you look at a subspace. Let's look at an open ball. Open or closed ball in Rn. Right? Let's say centered around 0. How do you get 2 points here? You join them by a straight line. It will always lie there, right? So there might be, this is one curve, but there will be several paths, right? So instead of going there, you can actually go through center. Join here and then join here, right? You can go like this as well. What you need is just existence of one. But it's not unique. It may not be unique. Right? So this is example 1. But you see here, the path should be inside that set. For example, if you look at subset here, this is 1 and this is 1 inside R2. And you look at 1 point here, 1 point here. You can have a path in R2, but this path does not lie in this set. Right? So this here, this set, let's say, this set is not path connected. All right. Three. Sphere S A R is path connected. So the proof. So how do you prove it? Suppose this is a sphere. You look at 2 points in the sphere. And this is the center of the sphere. All right. Now you consider the plane passing through these 3 points. So you consider the plane maybe, yeah, let me try drawing. Passing through this points. So here, this plane will cut the sphere in a circular arc. In a circular arc. And of course, this plane would go and go down. Right, so it will actually cut in a circular arc, something like this, in a great circle. So this path will lie on the sphere. So this will be the path. All right. Yeah. So try proving that, or try to find the equation of this path. That is an exercise. But this is how to say it. All right. So next example. A star set, open set in Rn is connected. So what is a star set? So star set, so omega inside Rn is said to be star set with respect to a point x0 if the straight line joining x0 and y lies in omega for every y in omega, right? So it is, if you think of no, this is not going to work. So it has some kind of symmetry. So it should be star shaped with respect to this point. So if you want to join this one, this point from this side, you have this straight line. So to go from one point to other, you first join that point to the center, or the point with respect to which it is star set, and then you join the other point. This would be the curve, joining these two. Another example.
Sir, so the
Yes.
definition of, can you just a little scroll back a little to the definition of the star shaped graph? Yeah, it says
Yeah.
that with respect to
The
a
straight
point
line
x naught,
segment, a straight line segment.
for every y belongs to omega, the line segment joining x naught and y belongs to omega. So technically,
Right.
a star-shaped figure doesn't have to be like a star, right?
Oh, no.
Yeah. Okay. When
Definitely
you are
not.
drawing it,
So,
you
for
tried
example,
making
your
it
ball,
symmetric.
this one is a star shaped.
Yeah, it's okay. But when you are drawing it,
Right?
you made it symmetric. So I thought there must be. I mean, I may be missing something.
Oh, no. That's not needed. Actually, so anything kind of, so like this could be star shaped. So it should be like star shaped like this. So I mean, the symmetry is just this, the line segment joining just one point should lie there. Yeah, it should not be like star.
So could you give an example of a path connected set which is not star shaped?
Not.
A path connected set which is not star shaped.
So here it is, n minus 0.
Okay.
So yeah, is path connected. So you can bend it things up, and you just look at. I mean, it is more general, but you can actually look at it one curve, right? It is definitely this just cut a curve. It's path connected, right? Because we are looking at the one path only, and you can it may not be like balls, may not be like a star shaped. I think so. A path in Rn is path connected, right? So an exercise. So try this one. Prove that a path connected subset of Rn is connected. Okay. So this is one. Actually, let me call it two. First, so one will write one if A from AB. So this one. So exercise is to prove 6. AB to X subset of Rn is continuous. Then f of AB is path connected. Well, f of AB will be path connected, but I want to show you that f of AB is connected. I want you to show this one, okay? And then you prove that any path connected subset of Rn is connected. Any question? So connectedness, to understand connectedness, you need a little bit of work. You need some, you need to sit down and think a little bit. So it sometimes can be complicated. So the point is, here this side I have shown you to prove. you must ask whether the converse is also true. You must ask yourself. Right. So next time I will explain a little bit about this connectedness. Connectedness and one theorem about compactness. That will be the end of this part. We'll start differentiation after that. From next week onwards, we'll start differentiation. Any question here? Okay, so if there is no question, then let us stop here. Yeah, and of course I'll upload things which I have not uploaded quite some time.
So in last class, you said that you will pinpoint some exercise question, and we have to send. Did you do it, or like I didn't
yeah,
get it?
No, that I have not done yet.
Okay, I
So
thought I didn't get it.
I'll put it in the UE Learn only, right? Maybe
Okay.
I can do it after I give one more assignment.
Okay, sir, I was like, I thought that I'm not getting it, so I asked.
Oh no, that is fine.
Okay.
Definitely. Yeah, recordings and notes will be uploaded tonight itself. Yeah, that I remember. I was just quite lazy for some time. Syllabus for that will not be a test, it's quiz. So quiz after the quiz we have taken, so it's after that. So mostly this last part of compactness, connectedness, and these things. Okay then, see you.
Okay, sir.